Hello, everyone, and welcome back to your channel of Math and Engineering Made Easy. In today's session, I would like to go over how to draw a shear force and a bending moment diagrams. And just a word of caution for those of you who are not in the States, because if you learn, like myself, the British way in Egypt, that's what the method we use, is that when you draw the bending moment diagram, we consider if the bottom of the beam is under tension, we consider that positive moment, and we draw it near in the direction of the bottom of the beam. In other words, if it's positive, we draw it under the center line. If it's negative, we draw it above the center line, which may be confusing to most. I don't know what you are watching from, but in the States, we do it like positive is above and negative is below. Which is common sense, to tell you the truth, even though I learned it the other way. So, and that would make things easy, because now the shear, as you will see, is the integral of the weight, and the moment is the integral of the shear. And even though you are integrating, you don't need really to use the integration method or the section method. I'll show you that it's much easier than that. Of course, you know how to do it. You should know how to do it if you were asked to use one method or another. But that's not the topic of my session. I was going to show you how you can easily find the shear force and the bending moment diagram. And I prepared a couple of examples from online, very simple ones. Maybe I thought maybe I will give you a frame, but maybe another session. So here is my beam. It's a cantilever beam because there is a fixed support on the right. So you don't need any more supports. If you add the support, your system or your beam would be statically indeterminate, meaning using statics alone, you won't be able to find the reactions at the support, and you will need look at the deformations and use some more advanced stuff that usually you cover in strength of materials course. So here we will assume that we have statically determinate beams, and that's what we are going to do. So I will draw the free body diagram. I tried to write the dimension, and it went very low. I'm sorry. So this 3 meter is just the distance of the distributed load. So I have a distributed load of 20 kilonewton per meter, and you know distributed load meaning it's not concentrated at a point, but it's split, in this case, evenly. It may be triangular, it may be trapezoidal, it may be anything. It may be circular, half a circle, any function, because you will be integrating it. But in this case, it's a very simple distributed load. So just in order to find the reactions at the support, we are going to replace it with a single force. I'm going to draw it maybe with a pencil, so you know it's with dotted lines, so you know it's not an extra concentrated load. It's just for the purpose of finding the reaction, not drawing the shear or the moment. No, you cannot do that. But for the purpose of calculating the reactions, I'm going to say, okay, 20 kilonewton per meter, meaning every meter is carrying 20 kilonewton. And if there are 3, that is a 60 kilonewton exactly in the middle. So this distance would be 1.5 meter, and that distance is 1.5. Okay, so I'm going to draw the free body diagram on another page, another piece of paper, just because I don't want to, the calculations, I don't want it to be with the diagram so you can see what's going on. So here, all what I'm going to do is to show the loads, the 20 kilonewton per meter, not 3 meter. And then I have a 40 kilonewton force going up. And then at D, there is the support. I'm not going to show anything on it here. I'm going to get a fresh piece of paper. I don't need to draw it in scale. I'm just going to draw a straight line saying here is the 3 meter Oh my God, I don't know what's wrong with this LED. Okay, and then here at D, I have potentially a dx, a dy, and a counterclockwise moment, m moment at D. Okay, so this is a free body diagram, meaning I took the supports, which is one support, and replaced it by the potential internal reactions. This is 20 kilonewton per meter. Again, the first equation, you can just ignore it. All what we have to do is to say the summation of the forces in the x direction should equal 0 for equilibrium. That's basically what Newton has said. If the string is stable, it's not moving right or left or up or down, it means that the acceleration is 0, F equals m times a, so the forces equal 0. And many people prefer to show that an arrow with a positive sign, meaning all the forces that point to the right, I'm going to consider it positive, like the positive x, and to the left would be negative. So here, this is vertical, only dx, so you get dx equals 0. Yes, we don't have a dx. We know that. We didn't need to make calculation. Also, I'm going to say the summation of the forces in the y direction equals 0. Here I can do the forces in the y because there is only one support. If I had two supports, it's better to take the moment first and then do the sum of the forces in the y next. You know, it's just to save time. But so here I have 20 times 3 is 60, like we said before. So negative 60 kilonewton plus 40, because it's going up. And I assume dy is going up, so plus dy equals 0. Notice this is dy minus 20 equals 0 to save your time. dn equals 20 kilonewton positive, meaning it's going up. And finally, I find the moment md, so I'm going to say sum of the moment about point D. Okay, that's the only, because, you know, I can take the moment anywhere, by the way. I could take it about this point, that point, doesn't matter in this case. But common sense would say take it around D. So you get rid of dy. dy is not producing a moment. Instead of having 3 terms, you only have 2, meaning the constant. So I have 20 times 3, remember, 60, times the distance, which is 2, and 2 and 1.5. So 20 times 3 times, and again, counterclockwise is positive. And this is rotating counterclockwise, so it's a positive moment. 20 times 3 times 5.5. But then I have the 40 kilonewton is going clockwise, so it's minus 40 times 2. Remember, many students still commit this error and say, oh, 40 times 2 is positive because the 40 is pointing up. I'm not calculating forces, I'm calculating moments. So you have to look at how the force is trying to rotate about D. If it's rotating counterclockwise, it would be positive. If it's rotating clockwise, it would be negative. And sure enough, this guy, the 60 going down, is rotating counterclockwise about D, but the 40 is going clockwise, so it's negative. Some students say, well, we are using digital phones, so we don't know what you mean by clockwise. I'm just kidding. But, okay. So, and then I assume MD is positive, so I say plus M sub D equals 0. 60 times 5.5 is 330. That's not the time now. Minus 80 plus MD equals 0. So MD plus 250 equals 0. MD equals negative 250, kilonewton meter, or 250 kilonewton meter clockwise. So these are the reactions at the support. I will come here at the free body diagram, and I will draw a 20 kilonewton going up and a 250 kilonewton meter going clockwise. It's a negative moment. Word of, caution here. When we draw the bending moment diagram, what we consider negative moment, so if I have a moment here going clockwise or counterclockwise, what we consider in the reaction as negative going clockwise, when I draw the bending moment diagram, I will say this is positive. Maybe we'll explain that later. And if it's going counterclockwise, which is a positive moment when I calculate moments, I will consider it negative here for the bending moment diagram. Okay? So be careful about that. Alrighty. So now let's draw the shear force diagram. We start at 0 because to the left of this point, there is nothing. So I start at 0. And then we say the shear force diagram is the integral of the weight of the loads. Okay? This load is constant. Constant. Oh, the shear is the derivative of the moment. So if it's constant, it means that the slope of the moment is constant. What does have a constant slope? Yes, it's a straight line. You can see that this is 60 Newton meter. Going from here it's 0, here it's 60, and it's decreasing as we go. So it's a straight line, and let's assume the 60, for example, is here. So this is 60 kilonewton, and I get that. From B to C, there is nothing. So I'm not adding to the integral. The integral stays 60, right? I'm not adding anything to it. And then the 40 kilonewton is called, do you know what it's called? An impulse. And the integral of the impulse, if you took like, Laplace transforms or something, it's a step function. So really, it's like I'm going up a distance of 40 to negative 20, because I am at negative 60. So 20 kilonewton. And then it's a step. So you go up 20 and you keep going horizontally straight until you find another step function, 20 going up. Of course, there is nothing after that. So you stop here at 0, and we start at 0 and at 0. That's the shear force diagram, and it's negative. See how easy it is? Constant, straight line. Nothing stays the same. Impulse, step function. Nothing stays the same. Impulse goes up. Of course, it's not drawn to scale, but if this is 20, that cannot be 60. But anyway. Alrighty, great. Now, how do I do the bending moment diagram? Well, the bending moment diagram is the integral. And you say, oh my God, should I have the equation of that line so I can, no. You learned that the integral of a function is the area under the curve, right? So I am here at 0. We start at 0 unless we had a couple. If we have a moment here, yes, I will start up or down, depending on whether it's rotating clockwise or counterclockwise, as we said. But if there is nothing, we start at 0 and we will end at 0 also. Well, that's a straight line, meaning a first degree curve. When I integrate it, it will become a second degree, meaning, and notice here, this is the slope of the bending moment diagram, because that's the derivative of the bending. So the slope is small, meaning I'm close to the 0, and then it gets larger. It's turning like that. Do you see? So now, we said the integral of this line from 0 to 3 will give me the area under the shear force diagram. Oh, that's a triangle that has a base of 3 meters and a height of 60 kilonewton. I say 1/2 times 3 times 60 is 90 kilonewton meter. So we say, okay, maybe let's say this is 90 kilonewton meter, but it's not going linear now. It's going, oh, let's make the 90 here. Okay. Then from here to here, it's constant, meaning the integral of a constant is a straight line. So from here to somewhere here, it's a straight line. But what is the value here? Again, area under the curve, 2 times 60. This is 60, not 20. Be careful. 60 times 2 is 120. 120 and 90 is 210. So this is negative 210 kilonewton meter. But the increment in the moment magnitude is linear. Oh my God. Okay. Then I will increase again, but at a slower slope. Here it was 60, right? And here it's only 20. And 20 times 2 is 40. So I will go down another 40 at a smaller slope as a magnitude, as an absolute value. And again, it's not to scale, but it shows me that I will end up with 250 kilonewton meter. Oh, guess what? The reaction at D is 250 kilonewton meter, is going clockwise, meaning I add it in the bending moment diagram, but the moment is negative. And that is the bending moment diagram. Of course, if you're drawing, say, with a pen, you will have to do this line to show that. Later, you will notice that if you consider the moment as a load, what? Yes, if you consider it as a load, then the bending moment resulting from that, if you divide it by EI, you get the deflection. Isn't that something? Yeah, that's what you are going to learn when you do the deflection of the beam, how far the beam would go down. There are many ways to do it. Slope deflection method. You can use the conjugate beam method, which I love. You can find that, but anyway. So for the time being, we are going to say, well, this is it. I found the shear force diagram. I found the bending moment diagram, and both are negative. Negative meaning the top fibers are stretched and the bottom are compressed. Notice that if you think about, say, a jumping, like diving board, the ones that are not fixed, you see that if you keep jumping here, it turns like that, right? It's going to turn like that. So you see that the top fibers, it's like when I showed you before, the top fibers, can I make it horizontal? No, you won't see it. It's not easy. When I'm not gonna break it, but when you turn it, you see that the top fibers are stretched and the bottom ones are compressed. Okay, so that's why we say negative. We draw it here. If you were following the British system, that would be a mirror image, like it will be, you will reflect it on the x-axis. That's the first example. The second example is here on the back. I'm going to start with a free body diagram again. The different colors show I have a 6 kilonewton. Here there is a 30 kilonewton meter, a clockwise moment that will be considered as positive in the bending moment diagram. And then I have 2 kilonewton per meter. And here there's a roller, meaning if I call this point A, B, C, D, E. At D, I will have a vertical reaction only. I'm not going to show if it's up or down. Let's do first the work here. Okay, so I have 6 kilonewton. Then here, oops. Okay, By. Notice from the sum of the forces in the x equals 0, there is no external horizontal force, so Bx equals 0. I'm not going to waste time on that. We have By, then here till the end, we have 2 kilonewton per meter, and midway, oops, I'm sorry. Why did I draw it on that one? 2 kilonewton per meter. And in the middle, I have also dy. We don't have x because that's a roller. And the distances are 3, 7, 3, 3. X, y. We are not going to say some of the forces in the x. We will start right away by taking the moment either about B or about D. So sum of the moment about point B equals 0, counterclockwise is positive. So if I take the moment about B, the 6 is rotating counterclockwise, so it's positive 6 times 3. Of course, the B doesn't rotate about itself. Then I have 2 kilonewton per meter times 6 is 12 kilonewton times 10. Do you see that the middle is exactly at D because it's 3 to the left, 3 to the right. So 2 times 6 is 12, and 12 times 10 is 120, but it's rotating clockwise. So it's minus 12 kilonewton times 10 meters. Okay, and then the dy is also 10, but it's rotating counterclockwise. So plus 10 dy, there is nothing else. Okay, yes, there is a moment. Why did I say there is nothing else? Where is the, oh, there is a 30 kilonewton meter, 30 kilonewton meter, rotating clockwise, so minus 30 equals 0. Notice here, I'm not drawing a bending moment diagram. I'm looking at the direction of rotation. So for purpose of calculating reactions, that's a negative moment, okay? So I have negative, so this is negative 150 plus 18 is negative 132 plus 10 dy equals 0, dy equals 13.2 kilonewton, and it's positive because I'm moving it to the right, meaning it's going up. Finally, I do the summation of the forces in the y equals 0. I have 6 going down, so negative 6 plus by minus 12, the 2 times the 6 again, plus 13.2 equals 0. So by, when I move them, this would be 18. And you subtract 13.2, so you get 4.8, also positive kilonewton, meaning it's up. So now I will go back here. So at By, it's 4.8 kilonewton, and this is 13.2 kilonewton. So let's do exactly like we did before. I have a 6 kilonewton going down. That's an impulse. So it produces a step function that goes to 6 kilonewton negative. And then it stays the same at negative 6 up until it comes here. And then it goes up 4.8, but it's still negative. It's still negative at 1.2, negative 1.2 kilonewton. And then that's a couple. It doesn't do anything in the force. Stays at 1.2 all the way till here. So this is 1.2 kilonewton. Then it will go down. Notice 2 times 3 is 6. So it goes down 6 to this point. It goes down 6 and 1.2. That would be 7.2. Somewhere here, I get down to 7.2. I want it to be slightly lower than this. And then it goes up 13.2. Notice 13.2 minus 7.2, it will go up to 6. Let's stop here. 6 kilonewton. And then again, that's constant, meaning the integral would be a straight line going down. 2 times 3 is 6. So sure enough, I go back to 0. This is a negative shear. That's a positive shear. Something I didn't mention previously in the previous example, but it's worth mentioning. You know that when you get, if the slope equals 0, that's usually it's what? Extreme value, either a maximum or a minimum. You see that the moment was 0 here, that's a minimum, there is no moment. And then it gets, I'm sorry, the shear was 0, so the moment has to be either maximum or minimum. In fact, here it doesn't do anything. And when you do a 0 here, and you get the maximum moment, negative 250, the derivative of that will give you the shear that goes to 0. In this case, the shear became 0 here. So the maximum bending moment we will encounter would be at this point. Let's see. I start here with 0 bending moment, 0 kilonewton meter. This is negative, and it's constant. So it's a straight line going down, and its slope is 6, right? 6 kilonewton per meter. But anyway, kilonewton. Now, this distance is 3, and 6 times 3 is 18. So the moment here would be negative 18 kilonewton meter. Careful. There is a moment, and the moment is clockwise, meaning it's going to increase. This is negative 18. When you add 30 to it, you get to positive 12. And the moment here is 12 kilonewton meter. Until it reaches this point, it will decrease linearly. A distance of 7 times 1.2 is 8.4. So you subtract 8.4 from here, you get 3.6. So I will get to a moment of 3.6 to this point. It drops down to 3.6, okay? And then it's gonna drop again. Notice that this area is a trapezoid. The two parallel bases are 1.2 and 7.2, so you average them and you multiply by the height, which is 3. These are 8.4. When you divide it by 2, you get 4.2, and 4.2 times 3 is 12.6 negative. So I'm going to subtract 12.6 from 3.6. I get to negative 9. So I will get to 9 kilonewton meter. Nine kilonewton meter. And then I'm going to go up. How much? 3 times 6 over 2. 3 times 6 is 18. Divided by 2 is 9. Going from negative 9 to 0, but it's not straight line. Notice here the slope is large and gets smaller. So it's very steep and then it gets smaller to zero. So this is a negative moment and then a positive moment and then a negative moment. Okay. And basically that is the bending moment diagram. So in this case, I give you a torque that is rotating clockwise. It could be rotating counterclockwise, but to show you what you do in that case. And I hope this was clear for you. And you see, it's really very easy. If you have a constant shear, that's a straight line and an inclined line in the bending. If you have a concentrated load, you get a step function. And if you have a distributed load, you get, first of all, in the shear, it's straight line, and then second degree parabola. If that was a triangular load, it would be a second degree parabola in the shear and a third degree parabola in the bending. And some students would say, so how do I find the area of the second degree parabola? Good question. Go back to the statics course and look at, I think in the distributed loads, I showed you, or no, in the centroid lectures, I showed you how to find the area of any degree polynomial, second degree, third degree, 10th degree, it doesn't matter. How do you find the X bar, the Y bar, and the area, okay? Alrighty, thank you very much for your time. I hope this was an easy session. And again, as usual, if you have any questions, please let me know by writing me a comment in the comment section. I'll get back to you as soon as I can. Thank you very much and have a great day. Bye.